So here we have a Riemann sum, and the notation looks kind of crazy, but we know that it's going to represent the areas of a bunch of rectangles that are approximating the area under a function. So I'd like to start this problem by coming up with an n value. Just say n equals 3 maybe. And let's see what this sum turns out to be. If we start at I equals 1, our first term in the sum is 5 plus 1/3. If we then go to I equals 2, our next term is 5 plus 2/3. And our last term would be 5 plus 3/3. And maybe it'll help you and maybe it won't, but I distributed the 1/3. And each one of these three terms is going to represent the area of a rectangle. The width of each one of these rectangles appears to be 1/3. And the height of these rectangles seems to be starting at 5 and increasing by 1/3 each time. So if I was going to draw a picture of this situation, it looks to me like we have some function starting at 5 and ending at 6. So maybe something like that. The width of my first rectangle is 1/3 and the height of my first rectangle is f plus 1/3. So something like that maybe. The width of my next rectangle is 1/3 and the height of my next rectangle is 5 plus 2/3. The width of my last rectangle is 1/3 and the height of my last rectangle is 5 plus 3/3, which is just 6. So this Riemann sum that we've written out here represents the sums of the areas of these three rectangles, which approximates the area under this function right here, which I think we can find between the x values 0 and 1. Now if we go out to the general case where we have n subintervals, this is really going to represent the same thing. This 1 over n out here represents our delta x, or the width of each one of our subintervals. We can see that that is 1 over n, which suggests to me that our b minus a equals 1. That numerator being 1 suggests that the width of our interval is 1. This piece right here to me says something about the function that we're trying to approximate the area under. While this was not really drawn to scale, you can see that the slope of this function is 1 over 1. So the slope of this line is 1, and its y-intercept is 5. And we know that the equation of that line is x plus 5. Or you could have written it 5 plus x to kind of keep things in order. Now when all is said and done, what we have is a Riemann sum that is approximating the area under this function between x equals 0 and x equals 1. If we take the limit of this Riemann sum as n goes to infinity, that gives us the exact area under this curve, and that exact area is represented by a definite integral. That integral is from 0 to 1. The function is x plus 5, and the integral is with respect to the variable x. So I think that that is going to be our answer. And that answer is great, but there is another way to interpret this same sum. Instead of seeing this function as 5 plus x, we could have interpreted this function as just some x value that increases from 5 to 6. In other words, I could have drawn this picture another way. I could have drawn a picture of the function f of x equals x and looked at the x values from 5 to 6, split up into three partitions. My three rectangles would look something like this right here, and those three rectangles would be exactly the same as these three rectangles that I drew here. So yet another interpretation of this problem could have been that the function that we're trying to find the area underneath is just the function x, and we're looking at x values between 5 and 6. And these two areas, these two integrals, would be the exact same thing. So I imagine this all seems a little bit mysterious, and I think that's for good reason. This is pretty tough material. But mull over this video for a little while, see if you can make sense of it, watch it a few times, and then we'll see if we can get a little bit more practice.